to more examples. So common types of mat foundation. So then mat foundation actually sometimes is also called raft foundation. So bear that in mind. Basically used when there is a weak soil and you need to increase to spread the pressure or the stress induced by structures over a large area. So by reducing, because we know that stress in the basic equation is P over A. So when you increase A, of course, when A goes up, then stress goes down, and that's what we need, because of course weak soils have lower Q ultimate. Q ultimate have lower uh, Q ultimate, which is the bearing capacity. So that's the point. So we can say that is a combined footing that may cover the entire area under structure. So it's a large foundation or footing supporting several columns and walls. Mat foundations are sometimes preferred for soil that have low bearing capacity. I already said that, but will have to support high column or wall loads. Under some conditions, spread footings would have to cover more than half the building. So you can get from the sense that also you need a large space, a lot of space. So a mat area, I mean under the mat footing, and then has several columns. You can see 1, 2, 3, 4, 5, 6, and so on. So these are all manner of mat footing or raft foundation, if you wish. So then the mat foundation can be more economical, especially if more than half of the building is covered, then can be economical. Several types of mat foundations are used. Some of the common ones are shown already from the previous. These are common types of mat foundation. So there is the flat plate, and so flat plate shown in this is flat plate. Then you have we can have flat plate thickened under columns. Point B. You note the difference. So this is the plan. You may not see the plan, so you can see the section, some difference. So under the columns, there is additional thickening. Or we just have one flat footing with a uniform thickness as shown. But here, under the footings themselves, I mean not the footing, under the columns, there could be additional thickening. And then we have beams and slab. This is shown in 10C. So in addition to this is what we see here. In addition to the mat foundation or raft foundation, you enforce. So along the this you put columns as well, and not columns, sorry, beams as well along the both ways. So you kind of put beams to tie the structure. So this is what we are saying. So that is for part 3. So beams and slabs, the beams run both ways and the columns are located. I don't know, you see, the columns are located, saying that these are the beams, right? Beams, and then the columns are located at the intersection, more or less what I've done before. So that's it, that's what we're saying. And So flat plates with pedestals, figure 10D, slabs with basement walls are part of the mat foundation. With the walls act as stiffeners. So uh, this one, uh, number 4 is flat plates with pedestals. So yes, so kind of adding some parts here. You can see here. So I mean you can notice the difference between this and this. So you can know what the normal mat footing is the one shown in black here. So this is the normal uh, mat footing, but you add some pedestal. So this is what you're saying. Then you can have some walls. You can have uh, additional walls on the mat plate as shown. So that's a different kind of or some way of enhancing the mat footing. So slab basement walls as part of the mat foundation. The walls act as stiffeners. Actually, this is sometimes even when you do what we call deep excavation. So once you do the base, then the walls the walls remain. You don't demolish. This idea is basement walls become part of the foundation. This is the same idea when you're doing, for example, you're doing in Kenya. We don't have a lot of deep excavation, I believe, I guess. But sometimes, if you want to put your some structures, normally you do you put what is called walls here. These walls are supposed to support, because otherwise in weak soils, if you don't support the walls, then the excavation will collapse. So you have what is called retaining walls. You design the retaining walls. Sorry. The ret- okay, you have that, and once you do your foundation, not foundation excavation, uh, those those becomes your retaining walls, such that this is maybe the bottom of your excavation. So these walls are designed because, as we have noticed, or we've said before, and I believe you have done a lot of soil mechanics and geotechnical engineering. If you draw uh, the the if you draw the stress distribution as you go down, is like that. So the pressure, the lateral force applied to the wall increases as you go down. So because of this, if you don't support this with a retaining wall, let's just call it a wall, in weak soil, the soil is bound will collapse. So what you do normally, design a retaining wall. Retaining wall could be a sheet pile sometimes, but sometimes you could use reinforced concrete. So once you use reinforced concrete, normally the function is just to support the excavation, so that it doesn't collapse. But after so for example, sheet piles, after you finish, you can remove or withdraw once you put a proper foundation. So sometimes uh, people don't withdraw or remove the wall, so that wall becomes part of the foundation. It's the same idea as the slab wall. So the basement wall forms part of the mat foundation just to stiffen and make sure the structure is stiff enough. And as if this, the idea here is we said if you've done steel, I don't know how much steel design you have done, but there's always some principle that if you have some stiff material, the stiff material, so this is the stiff material, and you load as and you load with some load, this will distribute the sorry, this will distribute such that this is in the ratio of 2 to 1. 2 to 1. The same idea here. So that is the function of stiffness, 2 to 1. So in a nutshell, this load will be transferred over an area. So if this area is L, just a minute. If this area is L1 and L2, so you can see L2 is larger than L1. So that's the idea, so that the structure is stiff and it can transfer the load over a larger area. This is the same idea with when you're doing hard. It's called hard pan. When you, for example, sometimes you see many times actually very common in when you're dealing with soft soil, you first put rocks. That's the idea also, because the rocks will make something that it looks like a hard pan. The same idea. So you put rocks. So this rock will be as in relation to for example, the stiff ground. I will be very stiff. So the rocks will help distribute the load in the same manner. This is what we're saying. We are saying again the idea 2 to 1, so that the overall area under which the load is transferred is much larger, and we reduce the stresses on the ground. So mats may be supported by piles, which help reduce the settlement of a structure. We're going to talk about pile foundation much later, built over highly compressible soil. So because a mat foundation is suitable, like we've said, for weak soils. So if you combine, because also piles are good for weak soils. So if you find soil that is very weak, probably very, very low shear strength, then you combine the two, because both of them are good for use in weak soil. So a pile is one good or effective way of carrying loads in weak soil. Another one is mat foundation. Except mat foundation, you need a lot of space. So if the soil is weak, you can combine the two. You can use mat foundation carried by on piles, and you can think of reasons why that can be. One reason is you may not have enough space for the mat. Of course, down when you're doing piles, the limitation is how much you are able to do an excavation, or how much you are able to drive your pile inside the soil. So unless if you, because it's an expensive process maybe, so you could be limited by resources or something like this, but you can combine. So where the water table is high, mats are often placed over piles to control buoyancy. Yes, there's also some idea that the piles actually, because water applies um, water applies pressure in all directions. Let me give you an example with a dam. A dam. So if you have a dam here, if you have a dam, this is this substructure. Okay. Uh, and this is your water level in the dam. This is the water level in the dam. So uh, water will always try to seep under the dam, and you use flow nets to do this kind of calculation, something called flow net. So what happens because of this? Sorry, because of this kind of behavior, uh, this there will be some force applied by the water as it moves up, because water applies pressure in all directions. There's an uplift, uplift force because of the flow, because of the seepage, which you can calculate. We just find the water head here, maybe it's 10. Then you find the water head there. Because as water flows here, it loses head. You can plot. If you did flow nets, you can remember this. And then you find the head there. Of course, the head is reducing because as it goes, it loses the head and there. And then you draw some shape. Normally, is a regular shape. Could be trapezium, could be a rectangle. Okay, let me try to show you. I'm trying to remind you, but it should be something you have done. If, for example, this head is 10, this head is 10, and these are the flow nets here. This is lost in how many equal head losses. So you count the number of flow nets. So from here, 1, 2, 3, 4, 4, and 5. So when the water flows here, the head would be 0. So this means the head loss in each of these compartments would be 10 over, sorry, 1, 2, 3, 4, 5. So the head loss in each of those would be 10 over 5. So to get the head here, to get the head at point A, and sorry, that's not right. So this is point A, B, C, and D. To get the head at point A would be 10 minus, there's only one flow net there, so it would be 1 times 10 over 2, sorry, 10 over 5 times 1. That is the head at point A. Head at point B, anyone who is concentrating, tell me. Head at point B is 10 minus, hello? Hello? Head at point B is 10 minus, exactly, yes. Yeah, that's good. So sometimes when you cannot, when the, for example, sometimes the flow nets do not exactly coincide with the corners. You can estimate. For example, uh, if the flow net was here, let me use a different pen. If the flow net was here, the flow net was there. This was your flow net. You use a half, so probably this is about a half, a quarter. You can estimate. Yeah, that's the point. So once you find the heads here, you plot as I've shown you, and then you find the area and multiply by the density of water, which is 9.81. That would be the uplift force, the force that the dam will experience. And then when you design the dam, you always find the factor of safety against uplift. Factor of safety against uplift, which is this uplift force divided by the anyone. Which force resists the ability to go up? Anyone? Hello? Factor of safety against uplift. Uplift is resisted by what? Yes? Yeah, you speak. Uh, Against uplift is usually the uplift force divided by the self weight. So that's it. So because it's also this what you're saying, and sometimes this can happen to foundations as well. So which help reduce settlement of a structure. So mats may be supported by piles which help reduce the settlement of a structure built over highly compressible soil. Where the water table is high, mats are often placed over piles to control buoyancy and figure the buoyancy is the ability now to float. Yeah. Figure 10.5 shows the difference between the depth df and the width of isolated footings. Let's see. You can have so the df, that's kind of the depth of this uh, protrusion under the column. And then so if you have if this is your, so the width, for example, you have a different enhanced depth under one each footing, and then the width of the footing B. So same thing highlighted in this in the photos. So this is kind of mat footing in reality in California. Is it California? Yes, in California. You can see some columns here, there. I believe, I think column here, here, columns there, there. So one big mat foundation, as you can see. So we cannot run away from the foundation we already laid. That we said that the QU is 1.3 CNC plus Q and Q. No, I think this 1.3 is a specific one for a specific factor for it's just a factor anyway, plus half B and gamma, uh, and gamma there's a factor there, I forgot, and gamma, okay, B and gamma, okay. Then for this is from Meyerhoff, decided that we need to modify this formula for the same formula. There is for compressibility, for the shape, and for the inclination of the load. So you add these factors. So this is for the shape. I think this is I is for inclination, and one D is okay. You can check your notes. There's one for compressibility of the soil, another factor for inclination, and another factor for shape. So then this is the reason for all these factors, but the same idea. The root of the equation is the Tizagi equation, as we have done, as we have proved before. So the previous equations give proper values of the bearing capacity factors as well as the shape, depth, and load inclination. So this is for depth. So sometimes, so when you then, for example, the soil is not compressible, then you don't have. There's another factor for compressibility. I think FCC for compressibility. You multiply in all these for all these. So for in this case now we are only considering the shape, the depth, and load inclination. Sometimes you can also modify for soil compressibility. So as shown in equation 6.28. So B is the smallest dimension. So what we mean is that when you have length times width sorry. So if you have a, let's say this one, L and B, okay, L1 and L2. So B in this case is L2, is the smallest dimension. This is what we're saying. And the net, so the net bearing capacity, you remember all this we talked about, minus Q. These are, uh, Q is the load, I mean, from the soil. This Q is gamma times dF, if you remember that. We've talked about that before. So a suitable factor of safety should be used to calculate the net allowable bearing capacity for mats on clay. The factor of safety, you remember we said before, ranges from 3 to 6, depending on the level of uncertainty. So the factor of safety should not be less than 3. We said that, but generally we said between 3 to 6. So the more you are unsure of parameters, the more is the factor of safety. So typically between 3 to 5. So if there are many factors that you are uncertain of, then you increase the factor of of safety to approach 6, so between 5 and 6. So under dead load or maximum live load, however, under the most extreme conditions, the factor of safety should be at least 1.75 to 2 for mats constructed over sand. A factor of safety of 3 should normally be used. Under most working conditions, the factor of safety against the bearing capacity failure of mats is very large. Is very large. Anyway, so we're saying the bearing capacity on sand, especially loose sand, is problematic. So this is what we are saying again. So we are saying 3. This means it's a kind of a higher value compared to 1.7. But we are saying in extreme condition, unless you are sure of a lot of things, then you use such low values. If, for example, the soil is stiff and has good bearing capacity, and so many things maybe within a determination, you're sure, then you can use such low values. However, for foundations, generally the factors of safety is between 3 to 6, and especially sand, the in loose sand cause problems. So once you determine the bearing capacity, you try to use a reasonably a large factor of safety against a bearing capacity failure. So for saturated clays with, I think this is phi. Sorry, this should be phi. So this, so for, actually this is phi prime. Phi prime is 0. So for saturated clays, phi is 0. Then the bearing capacity failure for Terzaghi is 5.14, and Q is 1, and gamma is 0, and the vertical loading condition. So in equation 6.28, so here, this equation, so NC here is 5.14, 5.14, and Q is 1, this is 1, but and gamma is 0. Okay, so you substitute in that equation. Once you do that, this is what you get. This is your ultimate bearing capacity. So based on this, then, excuse me, where Cu is undrained cohesion. So from previous table 5, phi, I think something is wrong. F, this is phi, not F. So the factor of safety, the modification factor for shape is this is can be evaluated as shown, and the modification factor for depth is can be evaluated as shown. And interesting, you should see that this depends on the length, the length and the breadth, where B is the least dimension, and this depends on the F and B. Just to refresh your memory, D, F, and B. So that's the meaning. So this so when you substitute in the preceding so you substitute these factors here, you have already solved these factors FCS and FCD. You can substitute back in the equation. So this is what you get, and the net. So if you subtract the Q, then the net bearing capacity is as shown. So when we have a factor of safety of 3, then the net allowable bearing capacity is as shown. So for maths in sand, since the factor of safety against bearing capacity failure is very large, the designs are governed by settlement considerations from equation 9.51. So given below with the N60, you remember the N60 we talked about? The N60, the N assuming 60% efficiency, and substituting in the allowable settlement for SE. So SE is the settlement. So for example, we've said the problem, especially loose sands, settlement. So you have to determine what is your allowable settlement. Normally, loosely should be governed by the length of the foundation. Is it the length of the foundation? So L. So uh, for example, you can say your allowable settlement is L over 25. I don't know, 25% of the no, the least dimension maybe. Depends on you. Anyway, most of the to make it easy, sometimes you can have rectangular footing, but mostly you have a square. So when you have a square, for example, then square would be LL. Then you can say your settlement would be L over 25. Yeah. So once you determine how much settlement you are going to allow, then the bearing capacity is limited to such values, where this is your settlement, and this is a factor. I think we are gonna. So this is the width. B is the width, and 60 we already know. SE is the settlement, and FD is I think FD is some factor. FD should be defined somewhere. Just a minute. You get the details in the notes. Is some factor. FD is some factor 1 plus 0.33 uh, B. I think B over L, if I remember. Anyway, is some factor. FD is some constant you get in the notes. Yeah. So, but these are empirical equations, just so you know. So, and then SE is the settlement in millimeter. So when B is large, assuming the uh, actually FD is this one. FD is the that Yeah, so that is the FD. That's the value of FD. So when the B is large, assuming dF over B is 1, the preceding equation can be approximated as follows. So still, and then in English, so as you can have this idea of we can have English units, or you can have, so the English at the foot, and then we can have the SI. So this is for the SI units. This SI, no, no, no. This is for the normal units. I don't know how to call imperial. Is it called imperial? So for imperial units, and this is for the English units, the ones who want to use feet. Definition of pressure on mud foundation. So if this is your the load, and that's your the depth dF, and this is the unit of the soil. So Terzaghi and Peck in 1948 suggested limiting the total settlement of pad strip footing to 25 millimeter. Yeah, so this is according to Terzaghi. So in this case, in the so here the for example, the if you decide the Terzaghi value 1 inch, that the your settlement would be 25. So then you put your SE as 25, and then this value would be 1. That's what you're saying. So Terzaghi and Peg suggested that we can limit the settlement for pad and steep foundation 25 or 1 inch, 25 millimeter, which would limit the differential settlement to 19 millimeters or 0.75 inch. However, the width of rough foundations are large than those of the isolated spread footings as shown in figure 8.1. I think we have shown the figure. Okay, in the previous, in typically we say, uh, I think in the notes that I already gave you, there's a figure 8.1. But anyway, the mud foundation we've already said is of a large area. So basically, you find the length and the width, which is the breadth, which is very high. But still, we are saying that, so as shown in the figures, the depth of significant stress increase in the soil below foundation depends on the width of the foundation. Hence, for a rough foundation, the depth of the zone of influence is likely to be much larger than of a spread footing. Of course, if for a spread footing, I mean for not spread footing, but for if this is the pad, so maybe the area of influence would be just around there. But if you have something this large, then you would have a much larger influence area. That's what we are saying. And so thus the loose soil pockets under raft may be more evenly distributed with further stiffening of the soil taking place, resulting in smaller differential settlement uh, based on this concept. So just to explain this a little bit. So if this is your soil, your that's the plan of the foundation, and soil is weak there, weak there, weak there, and weak there, and so on and so forth. And this, so you want to distribute the loading, the load over a larger area, so you help these pockets of weaknesses not to carry a lot of load. So that means you make the foundation, the pad foundation, stiff, such that when it is stiff enough, if this is your foundation plan. So if it is stiff enough, then this pocket will not carry a lot of stress. It will transfer the stress to this area, and this pocket probably transfers here and here. So if there is stiffness, then we can have kind of a stiff material. Then we can have what we can consider an even distribution of the load over the area, such as the weak place does not carry a lot of stresses. So that will limit what we call differential settlement, because, like I said before, uh, uniform settlement is good. Is For example, if this is your foundation, that's your foundation, and it settles uniformly. Uh, so it maybe after settlement settles uniformly. That's good. But if that's your foundation initially, that's your foundation initially, but it has what we call differential settlement. That is bad, because that induces a lot of moments and stresses on your in the structure. I believe you're in for Thea. There's some part of structures you've done that because of differential settlement. So if we have so to limit differential settlement, this is what was proposed by Tizagi and Peck. So based on this concept, Tizagi and Peck suggested in 1940 suggested for a maximum raft settlement of 50 millimeters 2 inches, which would still limit the differential settlement to 19. So we are lucky, because even though for raft, I mean for isolated pads we limit to 25 millimeters or 1 inch, and that limits differential settlement to 19 millimeters or 0.75. But because the raft foundations are large, so still, even if it's large, uh, because of the largeness and the stiffness, then still, even when you increase the settlement to 50, much larger, 2 inches, but still the differential settlement would still be 0.75. We are lucky because of the large length of the raft footing. So nowadays, even higher values are allowed for the limiting settlements. Ignore this. So even larger values can be allowed. So using this logic and conservatively assuming factor of safety, assuming FD, I think, let me confirm, assuming FD. So assuming FD is 1, we can approximate using the equations, I mean, these previous equations here. Using these equations, we can calculate based on N60. Yeah. And so when you use English units, the same idea. So this is when you use kilonewton per meter squared, SI units. Now when you use these other units, they call them the English units. So the net pressure applied on the foundation, C figure 10, we already talked about, may be used as, so this is that's what we are saying. So we say Q uh, net equals Q, which is, so the Q over the area, and you subtract the Q, or anyway, we express, so Q net is usually the Q, which is the bearing capacity, minus Q alt, let me say, minus Q. So minus, but this Q we are talking about is gamma times dF. So that's what we are saying. So where all these have been defined, and you should be very familiar with now. So to determine the net ultimate bearing capacity, maybe a question. The net bearing capacity of a mat foundation measuring 20 by 8 on saturated clay. So saturated clay, when you hear that, you should know phi is 0. And when phi is 0, you know that NC is 5.14. We've already talked about this before. Yeah, so, and then you have been given Cu. So from this, it's just a matter of substitution. If you allow me, in this form, in this formula there. So just to demonstrate how you can use 5.1 plus 0.195 over L. So 20 times 8, uh, L is the longest length and B is the shortest dimension. L is the longest dimension and B is the shortest dimension. So df, we have been given df to be 1 point. This is just a matter of substitution. So Cu is that, B is that, L is that, df is given there. So just substitute and you get your value. Should be no brainer. What will be the net uh, allowable bearing capacity of mat foundation with dimensions 45? So this is for you to do. You can convert into meters. I prefer that. But if you want to work in feet, you can knock yourself out as well. The average penetration is a number, and 60 equals 10. Is there a question? So in 1988, the American committee, they suggested a method for calculating differential settlement of mat foundation. According to this method, we find what is called rigidity factor. The all these You can find the rigidity factor this way, and then E is the modulus of elasticity of the material used in the structure. So if you're talking about concrete, that's E is now the so depending on the material used for the foundation, so E prime is for example, for concrete, and then ES is for soil. The B cubed is the length of the foundation, and I obviously is the modulus. The modulus of I is the second moment of inertia, either IYY or I. So for you, you should be very good with this, that if you have a length like this, B, D, the I would be dBd cubed over 12. Of course, depending on you, if you're bending like that, then this is true. But if you're bending like this, if you're bending in the x direction, if you're applying your loads that way, then the I would be dB cubed. dB cubed would be dB cubed over 12. So you need to note your the direction of application of force. Luckily, for in most cases, then this is the right way, the correct way of loading, because we are dealing with gravity loads. So IB is the moment of inertia of the structure per unit length at right angles to B. Right angles, yeah. So this is the B. So if that is B, you can see why this is a triangle. So if this is the B, should be easy to see. And then the length, okay, the term EB can be expressed. So because B, uh, the the foundation could be made of so many things. So we have to sum. So is the flexural rigidity of the superstructure and the foundation per unit length at right angles to B. And so also IB is the framed rigidity of the framed members at angles to B. The some of the the definitions there have disappeared, but you see in the notes, all this is just trying to explain all this. Uh, let me see. You can see them and I can't see them. This is the definition of the first one. This is that, and this is that, and A is the shear wall thickness. So, and then we can move on. And then the IF, summation of IF is the flexural flexibility of the foundation. So based on the value of KR, the ratio of the differential settlement to total length, settlement can be estimated in the following manner. So we just give you some values that you can use. So if KR is greater than 5, it can be treated as a rigid mat and the D is 0. If KR is 0.5, then D is 0.1. If KR is 0, then like this. And we give certain dimensions for B over L. So just some values that you can use. Some such issues in the field. There's a lot missing. I don't know. During the transformation, I don't know which. By the way, I did. Yeah. So let's see. Yeah. So yeah, most of the things seem to have been distorted, but this is much better. Yes. Yeah. You can see the previous one. We could not see FD. Yeah, but this one is, I think, much better. Some things were distorted. Yeah, this one has everything. Yeah, all the definitions you can see clearly. Yeah, okay. Yeah, so this is much better. So several field settlement observations for mud foundations are currently available in literature. So in this section, we compare the observed settlements for some mud foundations constructed. The equations that we talked about, equation 10.14, 10.15, these equations here. I think we already seen the equations about the settlement, the QNet. Then Meyerhoff in 1965 compiled the observed maximum settlements for mud foundations constructed on sand and gravel as listed in the table 10 and equation 10.14. If the depth factor, so just to refresh your memory, the equations we are talking about 10.14, 10.14, and 10.15. Those are the equations we are talking about. So this is the table we are talking about. So some values, I mean, just for your reference to use. And then we talk about compensated foundation. Now, figure 10.7, I believe I have it. 10.7, that's 10.8. So, figure 10.7 is where? Yep, figure 10 points, that's the figure 10.7. And equation 10.17, just uh, 10 equation 10.17, this equation here indicate that the net bearing pressure increase in the soil under mud foundation can be reduced by increasing the depth of the mud foundation. Yeah, I mean that's obvious. If we are saying Q net is Q U minus Q, uh, which is in other words Q times dF. So if you increase dF, then uh, you can increase the Q ultimate. That's what we're saying. This is Q net, sorry, Q net. So this approach is generally referred to as the compensated foundation design and is extremely useful when structures are to be built on very soft clays. In this design, a deeper basement is made below the higher portion of the superstructure so that the pressure increase in soil at any depth is small and relatively uniform. So the same idea, but we rearrange. So the factor of safety is the Q net over Q, and QU net is the net ultimate bearing capacity. For saturated clays, the factor of safety against bearing capacity failure can be obtained as shown for saturated. Remember, this is the Q net for this is the Q net for saturated clays. We already talked about this when and this is the so this is the Q net. You remember Q allowable net, and this is the Q. We've talked about this before. So so if we see figure 10.8, that's a figure, and then equation 10.17. Yeah, that equation. Then the net average pressure on the soil is that. So for no increase in the net pressure on the soil below mud foundation, Q should be 0. So if you don't want to increase the net pressure, then this value is 0. So therefore, uh, yes, okay, sorry. For no increase in the net pressure on soil below mud foundation, Q should be 0. So this value is 0. And therefore, the thus the depth would now be Q divided by the area. times the density, the soil density. This relation for DF is usually referred to as the depth of fully compensated foundation. The factor of safety against bearing capacity failure for partially compensated foundation, i.e., the depth over Q A gamma may be okay, maybe so. This is one example for you, and then you consider mat foundation of 30 by 40 in plan, as shown in 10. I don't know, figure 10.9. Okay, there's a figure. Okay, yeah, 10.9. The total dead and live load is 200. Estimate the consolidation settlement at the center of the foundation. This is something you should know. It's not part of the syllabus, but how to calculate consolidation settlement. You should have done, I think, in second or third year. You should know. So you can read through for yourself. Actually, the very simple. Just you need to know how to apply the formula there. The loading scenario here is just to help you to know how to calculate the overburden stress. So you note this carefully. Otherwise, the calculation of consolidation settlement is something you should already covered in s- in some other classes. So the structural design of mat foundations. This is important for engineers. So the structural design of mat foundation can be carried out by conventional methods. The conventional rigid method and approximate flexible method you can do with finite difference and finite element methods can be used. But the what we are going to do here is just the basic uh, concepts and some hand calculation. Now these ones are computer aided, which you can learn any software that can do design, be it structural uses. Most of them use finite element. But so in this case, we're just gonna do uh, the basic principles. So the conventional rigid method of mat foundation design can be explained step by step with reference to figure 10.10. Yeah, so with reference to that figure. In the conventional rigid method, the entire raft is assumed to be rigid. The bottom of the mat remains horizontal. The pressure applied to the underlying soil is assumed to vary linearly, and the mat is divided into rectangular beams, i.e. strip in both x and y direction, considering tributary areas. Each beam is analyzed as a structural member, and are and reinforcements are provided for the structural design consideration based on the bending moment and shear force diagrams. So this is basically borrowing from the knowledge of structures, and just to save you, some of you might already think this is very hard, but this is nothing, because the basic idea is stress is P, which now we are calling Q, sorry, Q over A plus PE the bending moment over I, PE over I. So, and you can have several directions. So, two directions. So, this is what we are taking. So, this is the formula actually we are making use of here. I think this is may not be complete because it should be plus or minus. So, plus or minus because we are talking about two directions. So, mat foundation, if this is a footing there, footing there, footing there, footing there, footing there, footing there, you know. So we are bound to have bending in X and Y. So this is what we are saying. That's all we are trying to do there. So the first step you're going to do is you have the mat dimension of length times B, and then the columns Q1, Q2, and so on and so forth. You add them because the load, the ultimate load would be the addition or the aggregation of everything. Then to determine the pressure is based on this formula, which I've said sigma or Q is QA plus PE over I plus PE over I plus or minus PE over I. But the bending can be either in the X or in the Y direction. So the reason for that. And then, so that is your I mean the typical mat footing, and then you assume it's we're talking about kind of a beam, and then you consider the bending in different directions, whether X or Y, and you you have to find what is called sometimes sometimes it's difficult. It's I mean it's all we are trying to do is find, for example, assume some, because this you need to find the first of all the centroid or the point of action of all the loads. You have to sum up. This is what we are doing here. So sum up all these loads, but where does that those loads act? That's a point. So you have to if, for example, the distance is x1 and there x2. I hope you get the point. So we say q1 times x1 plus q2 2 times x2 plus q3 times x3 plus all those things would be q, which is the sum of everything, times some distance which we are calling x bar. The same thing, x prime, sorry. The same thing now in the y direction. So if from there this is y1 and y2, something like this. So could be q1 times y1. You should already know this from physics. q2 times y2, q3 y3 plus all those things equals q times the y prime. That's what we are saying. So just to find the centroid. So that's all we are trying to do here. And then we are saying the eccentricity now would be the so for example, what we have done here, once you find the centroid is there, so the eccentricity would be, because this eccentricity here, this would be now the x bar that you have found minus the length over 2. I mean, should be, and then again the so that is the eccentricity in the x direction, and then the eccentricity in the y direction would be y prime what you have calculated minus let's this is be L over 1 L, okay, let's say Lx minus Ly over 2. That's all we are trying to do here. There. So it's also possible to determine Ex and Ey using xy coordinates. I mean, that is basic math. And then the Ix, so you have, because of bending, because of eccentricity, there will be bending in both x and y because of eccentricity. So if you are talking about the along the x-axis, the x-axis Iyy is this, but along the y-axis, let me use a different pen, So when we are talking about bending along the y-axis, then this is how to determine the second moment of area from your mechanics. So step 3, compare the values of the soil pressures determined in step 2 with the allowable net pressure to determine whether Q allowable or Q net. In what you are trying to do here, actually, once you know this formula, you're fine. Once you know this formula, you're fine. You're fine, except you need to know how to determine y bar, x bar, and you need to know that E x is x bar minus L over 2, and E y is y bar minus L over 2. That's it. So this, actually, these values are the eccentricity. When you do this, no, not the x. No, sorry. So once, so all these values are either, so this is for, will be Q E x, and this would be Q E y, and you should know that I y is LB cubed over 12, sorry, LB cubed over 12, but IX is BL cubed over 12. That's all. Once you know all this, you should not have any problem. Uh, unless now the issue is arithmetic. Okay, you can read all those things for yourself, and then you can draw the the more bending moment shear diagram, the bending moment and the shear diagram. Too many stories there. Let's go to an example, a real example here for you to see. So unless I need us to go slowly, I believe this is the last one. No, maybe, okay, some other things there we can study next time. But I'll end at this example, and I need you to participate. Okay, are you ready? Hello? Yeah, so for example here, you need to uh, so we determine, for example, eccentricity in the x direction. Let's start with the x direction. So the length of these things are also 0.5. So this is, so 0.5 by 0.5. So the eccentricity, you can see, is already indicated at 0.5 because the length of this thing is 0.5. So that is, so if we say x1, so x1 is 0.25. So we can say x1 is 0.25. I'm just going to sample such that you can get how to use, what to do, but I don't think we will do the everything, because then what will you people do? So anyone who can tell me what x2 is? We are talking about columns, so this is columns in this row. So x2 is this. X2 is from the edge to this. Anyone? I mean, it's obvious. You should not even think. So we don't know where the no, it cannot be 10 Buana. Yes, 10.25. 10.25. And x3, x3 is this to the centroid. How many? Sorry? No. X3, no. Yes. No, not 20.5. Not 20. Oh, yeah, yeah. 20, oh, yeah, 20.5. Yeah, you're right. 20.5. Now, for those who don't understand, you are looking at the midpoint of the midpoint. This the load is applied at the midpoint. Okay, and and uh, and this is 20. This is from the midpoint or midpoint of that is not midpoint. From the edge to the midpoint of that is 10, and then from this to that. No, no, no. It's not 20.5. Another guess? Not guess. Anyone else who is more keen? From the edge. Yes, 20.25. So anyway, let me try to explain what you are trying to do. And but this is something you have done. You should have done, or you have done, I believe, because you don't know where the center of the. So assume the Q is acting somewhere here. We don't know where. We don't know. This is where the Q is acting. So this distance is x from the edge, x bar, let's say. That's where the Q is. But we don't know where it is. So what you do is you say, for example, 550, 550, and all these, all the columns in that direction. So 550 plus 2000, 2000 plus 2000. I expect you telling me plus what now? 550 times, because all these are in the same length, so those ones times 0.25, 0.25 plus the columns here, all the additions of the 660 plus all that. So 660, I'm going to stop here because plus 2000 plus all those things times 10.25 plus, now this one's 470 plus all those things times 20.25. Now this, all that should be equal to the Q, the addition now of everything. 550, 2000, 2000, 550, 660, all this, the addition of everything there, let's call them Q times X bar. You know this already, this is what you don't know. You can calculate. Anyone with a problem? Should be simple. You do the same thing for the Y direction. Okay. Question? Silence means you understand. Class rep. If you have a question, you can ask. Yes. So you understand is okay. It's clear, right? Yeah. So, and once now you get the X bar. So for example, EX would be now that X bar minus L over 2. L over 2 is the entire length of the mat foundation. And then this, so the the now we're talking about the mx now. So mx, I don't know, I'm tempted to delete, but so for example, the moment in the x direction would be mx would now be the q, you know, the q which you know here, q times e, the eccentricity in the x direction, right? So, and y now would be the length, the this length. So if you're talking about the, so if you're talking about the x direction would be mx times y, where y is the is the distance of the centroid to just a minute. Okay, I'll be forced to delete this. Y is this distance. So if this is the centroid, if this is the centroid, I don't know where it is. Maybe here. I think here. If this is the centroid, then this y is this distance. Okay, y is that distance, and then x is that distance. Just a minute. No, no, no. Just x and y is the longest, eh? Just a minute. The now this sorry, this, yeah, is that distance, but it depends on, for example, the if you are talking about the here, the location depends on the location of the column. So here the x is from, from the, so if this is the centroid, that's the centroid. So that's the centroid. So that would be your x, x, and then, so I mean, it's the distance from the reference. So if you're talking about this column, that is your x, and if you're talking about the y, so the centroid. So now you can see here. So that would be your y. So if you're told to determine the the stresses, okay, the question you'll be asked mostly is that you determine the stresses maybe at point F, H, E, and so on. Now F is at the edge of the at the edge, at the final edge of the mat foundation. So the y and z, the y and x is, yeah. So So for example, at point A, let's see, at point A, the equation. Mhm. Yeah, yeah, yeah. But the reference, let me just show you. For example, at point A, we are talking about q over A, which is 26, minus 0.42x. What is x? X is, so the centroid, the distance between the centroid, I think, to the center here. So we've already determined the centroid is here. So the x, you can see, and you also have to choose which direction is positive. So you can see here is negative because the centroid is here. So the x is, so we are assuming the positive x is this one. So negative 10 uh, 0.25. So the distance between the centroid of the overall structure and the centroid of the column in question. Okay, so you can see, so that's negative 10.25, you can see here. Then the y is the distance now from the centroid there again, and the centroid of the whatever you're considering, the column you're considering, which in this case is, yeah, you can see there's, I believe this is 0.11, 0.11 up, plus 9, but f is at the edge, right? At the edge. So you add zero point 0.5, plus, is it point? Yeah, so yeah, so 0.05 times y. Y, I think, is 9. This is, yeah, you can see here now. This is 9 plus 5. This is 0.5, 9.5, plus, you can locate because this is already up here. 0.11 plus some length. So that's 13. So anyway, the y is this one. And no, not that. The centroid to the point you're considering. So yeah, to the point you're considering. Okay. So that according to this is 13.75, and it's in the positive direction. And for the x, because this is the centroid, this is going to be the negative direction. So just one example there. You can check the rest to see that you're able to understand. Question? Yes, class rep. What are you asking? Mm-hmm. Yeah, but remember the distance x or y depends on if you're asked where do you determine the stress. So for here, if the stress is here, so this to the centroid of the centroid, the values x and y. So whether you're talking about x, depending on x is the horizontal or the vertical direction, but with reference to this, and you're talking about the centroids rather than the centroids rather than the yeah. So here, so I think this is the centroid. Sorry, so this is the centroid. So because f is at the no, okay, f is at the middle point, right? So but if you are told at the edge, then you have to add the value point point you have to consider from the edge, depending on where you're asked to determine the stress from. I think that should be clear, and you interact with the example to you have a clearer idea. We can end there. Class rep, when is the next slot you're available?